Welcome back, class. Today we're going to start talking about what derivatives mean and how they came up in the real world. So I want to remind you, first of all, that derivatives are an attempt to capture the idea of slopes for functions that aren't linear. So just like slopes, a derivative measures how the output of a function changes when you change the input. Or, if you want to think about it this way, how fast or slow the output changes as you change the input. So there's an example of a derivative that you encounter in everyday life that you can always sort of have at the back of your mind. And that is something that shows up in a car. Namely, cars have what we call an odometer. And this measures the total distance traveled by the car. And so we can write this as a function, O of t, and this will be the number of miles on the odometer t hours after the car was born. So at t equals 0, this starts at 0, and as the car gets driven, this number goes up and up and up and up. And the key thing I want you to take away from this is that O prime of t, this is actually given by the speedometer on the car. So the speedometer nominally tells you how fast the car is going, but if you think about it, how fast the car is going is also telling you how quickly the total number of miles traveled is going up. And so if you really try and nail down, if the speedometer on a car says 60 miles per hour, what does that really mean? What is the 60 actually capturing? And what the 60 is actually capturing is that if the car continued at exactly the same speed for an hour, it would travel 60 total miles. The reason why we write this in miles per hour, or mph as it's usually written, is because the same thing could be true if instead of saying 1 hour, I said something like, if the car continued at exactly the same speed for 2 hours, then it would travel 120 miles. Or, if it traveled at exactly the same speed for 10 hours, it would travel 600 miles. Or, even I could go the other way, if it continued at exactly the same speed for 30 minutes, then it would travel 30 miles. And so there's this subtlety that goes into interpreting what the speedometer says at any given point that we really don't often think about, which is that it's really describing a rate that only has a meaning if you imagine that the car stays at exactly the same speed. But, of course, almost never in real life does a car stay at the same speed for even 10 minutes, much less for an hour or 10 hours or whatever. And that's why we use this term instantaneous rate of change when we talk about the speedometer or the derivative or whatever. Namely, what we're trying to do when we talk about the speedometer or when we talk about the derivative is we're talking about how a function is changing at one instant in time. Now, this might sound like a paradox, because if I talk about one instant in time, well, nothing is changing. Time is frozen. And so when I say the car is traveling at 60 miles per hour at this one instant in time, what I'm saying again is a little confusing. Because in that one instant, the car isn't traveling at all. This paradox is actually exactly the same paradox that showed up when we were trying to calculate derivatives, and we kept coming across this 0 over 0 thing. And then we used limits to fix this, effectively just to make sense of this idea. How fast is the position of this thing changing at this frozen moment in time? Now, calculus was invented to describe the laws of motion. So that is how things fall or move, gravity, etc. So I want to do an example very much in the spirit of what Isaac Newton was looking for when he invented this. So now let's imagine that we're running up to the top of a big tower and dropping a rock off of the top, as physicists often did during this Renaissance era. And let's say that the height after t seconds is given by this function. So we run up to the top of a 100-foot tower, we drop the rock, we watch how it falls. So what does the derivative mean in the context of this problem? Well, I can calculate the derivative. It will be minus 32t. And so I could calculate, for example, h prime of 1 will be minus 32. H prime of 2 will be minus 64. But what are these numbers telling us? Well, first of all, let's write down the units on each of these numbers. So each of these numbers is in feet per second. How do I know that they're in feet per second? The units of the derivative, just like the units of the average rate of change or the units of the slope, are always the units of the output of the function over the units of the input of the function. And in this case, the output of our function is the height in feet, and the input of our function is the time in seconds. So feet per second. And so feet per second, just like miles per hour, is a measure of speed. And so this minus 32 and the minus 64, these are measures of how quickly the rock is falling at 1 second and 2 seconds. And in particular, if you look in this example, you see the rock is falling faster after 2 seconds than it was after 1 second. And you can think for a moment and decide whether you agree with that. But if you picture dropping a rock from a high height and picture it falling, then you probably picture that as the rock falls, it falls faster and faster and faster towards the Earth. And so it makes sense, hey, the derivative at 2 is bigger than the derivative at 1. Note, by the way, these minuses are here just to capture the word falling. If these were positive, that would be saying that as time went by, the height of the rock got higher rather than lower, and that would not make much sense. Now, notice how, as we were talking about this, we were talking about how the velocity of the rock changed. Okay, namely, we said the rock goes faster as time goes by. Well, if we want to talk about how the velocity is changing, we can actually look at the derivative of the velocity, which would, in this case, be h prime prime, would be minus 32. Now, there's a name for this derivative of the velocity, or this measure of how the velocity is changing. Namely, we call this, the second derivative, we call this acceleration. And so if you think about what the word acceleration means in the context of a car, for example, accelerating means speeding up. Namely, it's telling you exactly, again, how the speed changes. Okay? And so that's what acceleration means in a physics context, too. It's how the speed is changing. And so here we have h double prime of t is, and in our example, it happens to be minus 32. And we've got to look at what the units of this are. So this is the derivative of h prime of t. So its units are the units of the output of h prime of t, which are in feet per second, over the units of the input, which are in seconds. So this is really telling you the change in the speed per second. However, physicists, I'll warn you, prefer to write this in this way. That is, they treat this feet per second as a fraction and just lump the seconds together, and so they'll write accelerations in the units feet per second squared. Or, if it's a physicist, more likely meters per second squared. Now, to give you a sense of how important this idea of derivatives is to the physics of motion, one way to state the law of gravity is to say that the second derivative of the height of any object in freefall is always negative 32 feet per second squared. This specific constant, this minus 32 feet per second squared, this is called the acceleration due to gravity. And if you see a physicist write this down, they'll much more often write this again in meters per second squared, in which case they'll write negative 9.81 meters per second squared. But this is very important, and this works for any object, no matter what the weight of the object is. And so you can throw the object up in the air, this will still be true. You can shoot a bullet out of a gun, this will still be true about the bullet. Whatever version of this you want, this is what the law of gravity says. Now, I should note there are a few provisos. So, first of all, this only works on Earth, because this is really the gravity due to the surface of the Earth. So if you go to a different planet, you will be lighter or heavier, as you may have thought of. So on the moon, you're much lighter because the moon weighs less than the Earth. Also, this rule does not take into account wind resistance, which is important for certain applications, such as skydiving, for example, or any form of air travel. To wrap up our discussion of physics, I want to summarize everything I just said in terms of 3 functions. So, first is we have position as a function of time. And so in our last example, that position was given by the height of the rock. But position could also be how far along a road a car is, or how deep underwater a submarine is, or there are a bunch of different ways to measure position, and what I'm about to say applies to all of them. Now, if you take the derivative of this, you get what is called the velocity. Now, I don't want to dwell on this technicality because this isn't a physics class, but there's a slight distinction between velocity and speed. And that distinction is that velocity tells you a direction. So in this example we just did with the rock, the velocity at time 1 second of the rock was negative 32 feet per second. The negative here is telling you the direction, namely the rock is going down in height. Okay. The speed of the rock is this minus the direction. So the speed of the rock at this time would just be 32 feet per second. No minus. So the speed is just the absolute value of the velocity, if you want to differentiate between these two words. And if you take one more derivative, then you get acceleration as a function of time. And so the physics of motion is all about the position of an object, which is then described by the velocity of the object, which is the first derivative, and the acceleration, which is the second derivative. And in fact, physicists even give a name to the third derivative of position, and so on. But ultimately, what is velocity? Velocity is how fast the position changes. And then acceleration is how fast the velocity changes. In general, it's always the case that the derivative measures how fast the output is changing. But I want to make one proviso about this how fast that adds a little bit of a wrinkle to thinking about the derivative in some other contexts. Namely, in all of these previous examples, the physics ones I just did, the input was time. And so when I say how fast, naturally when you see the word fast, you think of time. But when I talk about the derivative in general, and we talk about how fast, it's in terms of changing the input. And that input won't always be time. And so in the next video, I want to do some examples of talking about the derivative and what the derivative means, where the functions we're looking at are not functions of time, but functions of a different thing. But I'll wrap up this video on calculus and physics here, and we'll pick up in the next video and we'll talk about some other kinds of functions. But that's all for now. I'll see you next time.